Empieza tú y después les presentas a... ¿Sí?
¿Sí? Ok. Buenos días a todos. Yo soy la doctora Mayra Lebrón, profesora del Departamento de Ciencias Físicas de la Facultad de Estudios Generales y también la coordinadora de la celebración del centenario de la Unión Astronómica Internacional del capítulo de Puerto Rico. Nosotros hoy nos encontramos aquí en la Universidad de Puerto Rico, recinto de Río Piedras, para una ocasión muy especial. Contamos con la visita del doctor Del Ferguson, que nos va a estar dando una charla sobre Einstein, pero en particular quería yo mencionarle varias cosas sobre la celebración del año internacional de la Unión Astronómica Internacional, su centenario. Quería mencionar que esta organización es la organización más grande mundialmente de astrónomos profesionales. Reúne a más de 13.000 astrónomos profesionales y tiene pues, unos objetivos bastante particulares. Y en su centenario en particular, esta organización desea llevar la ciencia al público. Así que su celebración del centenario va a estar enfocada en hacer actividades de divulgación. Y nosotros en Puerto Rico, pues, obviamente nos vamos a estar uniendo a eso. Y esta actividad es parte de eso. El recinto de Río Piedras de la Universidad de Puerto Rico está uniéndose a la celebración con esta charla celebrando a Einstein en su también centenario de la primera prueba o evidencia de esa teoría de la relatividad general. Así que hoy vamos a escuchar sobre eso. Antes de iniciar con la charla en general, quería darle alguna información sobre la celebración del año de la astronomía. Para Puerto Rico, esta celebración va a contar con actividades de charlas como esta y otras más. Van a tener exhibiciones, vamos a tener observaciones astronómicas y quería yo mencionarles, que nos parece muy importante, que las actividades que se van a llevar a cabo no es una sola organización, sino en Puerto Rico vamos a estar trabajando en diferentes grupos, entre ellos obviamente el recinto de Río Piedras en su departamento de física y de ciencias físicas. Tenemos el apoyo del Centro de Recursos Educativos y Tecnológicos, lo que es el Círculo Astrofísico. La Universidad de Puerto Rico, el recinto de Mayagüez, también va a estar haciendo actividades celebrando el centenario. También tenemos el Ateneo Puertorriqueño, que también nos proveyó la actividad inaugural y va a estar haciendo actividades. NASA Space Grant, el Colegio de Física Fundamental Interdisciplinaria de las Américas, COFI, que también va a tener sus actividades. De parte de los observatorios de astronomía aficionada, ¿no? Astronomía que se hace para todo el mundo, tenemos el Observatorio Astronómico del Colegio San Antonio de Padua, la Sociedad de Astronomía del Caribe, la Sociedad de Astronomía de Puerto Rico. Y de otras universidades tenemos a Caribbean University y la Universidad Interamericana de Bayamón, además de Kennedy Space Center. Estas son organizaciones que al momento se han unido con nosotros en Puerto Rico para esta celebración. Les digo rapidito que otra charla que va a estar pasando próximamente, el 21 de febrero, en la Inter de Bayamón, va a haber la charla concurso de Budapest en el sistema solar, asteroides más allá de Neptuno. Se van a hablar de asteroides que tienen anillos. Los invito a todos a esta actividad. También vamos a tener noche de observación. Les anuncio rápidamente que este sábado 9 de febrero en el Centro Ecoturístico del Este, eso es en Ceiba, van a haber observaciones astronómicas abiertas al público, libre de costo, por la Sociedad de Astronomía de Puerto Rico. Están todos sumamente invitados a esas actividades. Y obviamente vamos a tener actividades celebrando los 50 años de la misión Apolo 11 a la Luna. Y tenemos también un programa que es de parte de la Unión Astronómica Internacional y nosotros darle las bienvenidas a todos, quería darle un pequeño introducción de cosas que van a estar pasando. Vamos a tener ahora al estudiante Luis Flores, que va a dar una introducción a nuestra conferencia de invitados antes de comenzar la charla. Le damos la bienvenida. Bienvenidos todos. Gracias.
Gracias por estar con nosotros hoy esta mañana. Voy a estar comunicándome en español, luego voy a traducir al inglés para beneficio de todos. For English speakers, I will be translating. Mi nombre es Luis Flores, soy estudiante graduado de física aquí en la UPR y también miembro del Círculo Astrofísico de Puerto Rico. Como bien mencionó la doctora Mayra Lebrón, este año estamos celebrando el centenario de la Unión Astronómica Internacional, quienes miembros se dieron a la tarea de unificar el mundo para la exploración del universo. Hoy tengo el honor de presentar al Dr. Ateneo Ferguson, quien ha tenido afinidad por Puerto Rico desde que fue miembro del Observatorio de Arecibo hace 40 años. El Dr. Ferguson recibió su doctorado en astronomía de la Universidad de Arizona Tucson en 1974, donde estudió bajo la mentoría de W.J. Fogg, quien descubrió el pulsar óptico en la nebulosa de Cangrejo, y Bart Bok, quien es reconocido por su trabajo en la estructura y evolución de la galaxia. El Dr. Ferguson ha tenido una carrera extensa como profesor en las universidades de Arizona, Louisiana, New York y Missouri, y como investigador en el Instituto de Radioastronomía de Max Planck, el Observatorio de Arecibo, el Centro de Investigación Glenn y el Centro de Vuelo Espacial Marshall, ambos de la NASA, y recientemente en el Laboratorio Investigativo de la Fuerza Aérea. Es autor de varios estándares de diseño de la NASA y ha realizado experimentos en los entornos de naves espaciales, el transbordador espacial, estación espacial y el Mars Pathfinder Sojourner Rover. Su primera publicación fue sobre la rotación aparente de objetos con movimientos rápidos, en donde se observan efectos relativistas. Hoy, el Dr. Ferguson explicará brevemente la relatividad de Einstein y algunas de las observaciones que se han realizado para medir los efectos relativistas en su presentación titulada Einstein, Ericsson and Me, 100 Years Passing the Test. Voy a traducir en inglés. Morning everyone, my name is Luis Flores. I am a graduate physics student at UPR, a member of the Astrophysics Circle of Puerto Rico. This year we are celebrating the 100th anniversary of the International Astronomical Union, which members took to the task of uniting the world to explore the universe. Today, I am honored to introduce Dr. Dale Ferguson, who has had an affinity for Puerto Rico ever since he was a staff member at the Arecibo Observatory 40 years ago. Dr. Ferguson received his PhD in astronomy from the University of Arizona Tucson in 1974, where he studied under W.J. Fogg, discoverer of the optical pulsar in the Crab Nebula, and Bart Bok, who is recognized for his work on the structure and evolution of the Milky Way galaxy. Dr. Ferguson has had a far-flung career, teaching at the University of Arizona, LSU, NYU, Southeast Missouri State, and has done research at the Max Planck Institute for Radio Astronomy, the Arecibo Observatory, NASA's main research center and Marshall Space Flight Center, and most recently at the Air Force Research Lab. He is author of several NASA design standards and has made experiments in spacecraft environments, the Space Shuttle, Space Station, and the Mars Pathfinder Sojourner Rover. His first scientific publication was on the apparent rotation of a rapidly moving object, which is a relativistic effect. Today, Dr. Ferguson will briefly explain Einstein's relativity along with some of the observations that have been made to measure its effects in his presentation titled Einstein, Ericsson and Me, 100 Years Passing the Test. Let's give a warm welcome to Dr. Dale Ferguson.
Thank you very much, and welcome, and I'm glad to see some people here. And I want to, before I start, acknowledge that this would not have been possible if I hadn't got a 6-month grant to work at Arecibo from the Air Force Office of Scientific Research. So, and maybe I've being a little bit optimistic, putting myself in with Einstein and Eddington. But I thought there might be some interest in maybe making it a little more personal than just, you know, here's these old guys that are not around anymore and they did this and that. Well, I'm still around and I'm doing this and that still. Right? Okay, so, of course, this is because, I'm giving a talk because this is 100 years since Eddington actually confirmed Einstein's general theory of relativity by seeing light being bent as it went by the sun. We'll talk about that in a minute. Well, first I want to start off with some pictures of Einstein. Some of these you've seen many times, others you may not have seen. There's Einstein as a young man. That at the bottom of the picture you can't see it, but it says 1913. So that's what Einstein looked like after he had formulated the special theory of relativity, but before he had formulated the general theory of relativity. So he was a good-looking young man, and as he got older, I don't know if you consider him good-looking or not, but he did have a sense of humor, and that's what that picture down at the bottom is about. Okay. Einstein was born in 1879. It seems like a long time ago, didn't it? He was destined to become the world's most famous person. Actually, there were surveys that were done in the early 1920s, and he was more famous than anybody else in the world. His name became a household word. One of the greatest physicists of all time. And he and his picture became synonymous with wisdom. In fact, they modeled Yoda's eyes in Star Wars after Einstein's eyes because he was known to be wise. His theories at the time were considered outrageous. People have been trying to prove them wrong for 100 years now and have not succeeded. In fact, they've been proven time and time again, and all of modern physics depends on his theories of relativity. Now, some people would say, well, quantum mechanics doesn't depend on theory of relativity, but quantum mechanics actually does depend on the theory of relativity. In fact, in order to show this, Paul Dirac had to formulate quantum mechanics in terms of general relativity. Okay, it all began before Einstein was famous, when he was only 8 years old, when a famous experiment was done called the Michelson-Morley experiment, after the two people that did the experiment. And it is an example of what we call in physics a paradox. They were expecting to get certain results from the experiment. In fact, they had to get these results, or all of physics would be wrong, and it turned out they got a null result. So we'll talk a little bit about their experiment and then go on from there. The experiment was to measure the direction and speed of the solar system through what people considered the medium of light transmission in those days, something called the ether. Ether was supposed to pervade all of space, and light actually traveled by waving in this medium, the ether. They used an interferometer, which is an instrument that measures interference of light. I'll show you a picture of it in a minute. The idea was that when the light was traveling in the direction opposite the ether, it would be slowed down. And when it was traveling in the direction that the ether was moving with respect to the Earth, it would be sped up. Okay, and by measuring the speed of light, then you could see what the motion of the Earth through the ether was, because we were the Earth is moving through space. Everybody knew that and still knows it. And this is what was called a null result in physics. It's when you get no result, neither positive or negative. It just didn't work. And so the question was, what was wrong with our thinking? Either the Earth was not moving, nobody was willing to believe that, or that light was neither impeded or helped along by the Earth's motion through the ether. No one was willing to accept that either. And according to Newtonian physics, neither possibility made any sense. And so that's the paradox. How could they have come up with this result, which was contrary to all of physics up to that time? There's Michelson up there in the upper left. Morley, who's not as well known as Michelson, is down just a picture below. They worked at the Case School of Applied Science, which later became Case Institute of Technology. That's what it was when I was there. And it became Case Western Reserve, as it still is now. Only they've now branded it Case. So now it's just Case. Anyway, this experiment was done in the basement of the main building of the Case School of Applied Science in Cleveland, Ohio. You can see the experimental setup there. That's a big slab of sandstone. They used that to make sure that nothing would move relative to anything else in the experiment. You can see there are places where mirrors are set up there. There was a light source and so on. Now, to give you a little bit of my background, I did my undergrad work at Case. I graduated in 1970, and one of my professors was R.S. Shanklin, who was an expert on the Michelson-Morley experiment. So I got firsthand a lot of information about the Michelson-Morley experiment. Okay, here was the experiment. It uses an interferometer, and an interferometer is where you cause two different paths of light to interfere with each other. When they interfere with each other, there are fringes that are set up. As you know, light waves can interfere with each other. Here was the white light source in their experiment. Light would come out and bounce off. This is, what was it called, a beam splitter mirror, or a half silvered mirror, which actually split the light into two different beams. So one of those beams went up like this, came back down, and was observed down here after it had interfered with the second beam, which went through the beam splitter, hit this mirror, came back down to that same point, okay, where it interfered with itself, and that's the interference pattern that you saw. And you can see it's very colorful. This is the same kind of colors that you see when there's, you see an oil slick or something like that, where you see many colors on, adjacent to each other. This was the pattern that he saw. Now the ideal was, that big table that he had this on was actually floating in a pool of mercury. And what he could do was, what Michelson and Morley did was they turned this around so that they could vary the direction that the light was moving with respect to the Earth's motion through space. And so they expected to see the interference pattern change because the time it would take the light would be different in a different orientation. So when the light was going in the direction, same direction as the Earth, it would be different than if it was going in the opposite direction. So that was the experiment. And it should have shown that this so-called ether wind that's caused by the Earth's motion through the ether. Oops. Wrong one. Since it did not, then somebody had to figure out why it did not. Okay. Now I'm going to switch gears here and go over to a discussion of Einstein, because this was the explanation that now is accepted for this is one of Einstein's theories of relativity, which he came up with, special relativity he came up with in 1905. He was 26 years old, okay, young man. In that year, he wrote 4 papers that were all considered major achievements and really revolutionized physics in 4 different areas. First one was about the photoelectric effect. I won't talk about that. Second one was about the Brownian motion. I won't talk about that either. You can Google these things, right? The third was the theory of relativity, and then the fourth was a consequence of the theory of relativity, that the most famous equation of all time, of course, E equals mc squared. Now, interestingly enough, when Einstein got the Nobel Prize in 1921, it was not for relativity. It was for the photoelectric effect. So look that up in your Funken Wagnalls. Okay, here's special relativity, an introduction. That's actually Einstein's handwriting up there in the top, where he first derived E equals mc squared. I don't know how many of you read German, but it's, you can see that even Einstein made mistakes and had to cross them out. What this did was it hypothesized effects of the motion at very high speeds that were close to the speed of light. And special relativity, as opposed to general relativity, special relativity is only strictly valid for uniformly moving or stationary inertial reference frames. An inertial reference frame is one that's not being accelerated. So we'll talk about that a little bit too. His postulate was, and this is what Michelson-Morley experiment said, was that the speed of light is constant for every reference frame, regardless of its velocity, relative to other reference frames, or to this hypothetical ether. Okay. And by assuming that, you can come up with some reasoning that will tell you in the end that E equals mc squared. I have to tell you that my first scientific paper was my undergrad thesis in 1970 was on a special relativistic effect, the apparent rotation of a rapidly moving body. In other words, a rapidly moving body will not appear to be in the same orientation. It appears to be rotated, and that's a relativistic effect. Okay, so here's the postulates of relativity. First of all, if you've got a physical law, it has to be valid in any reference frame because there's no preferred reference frame. There is no ether. There's nothing that's, quote, stationary. Everything is relative to everything else. Okay. And the second is that the speed of light, and this is, everybody says always in a vacuum, which is where the speed of light really is constant, is the same in all these reference frames regardless of the motion of the light source. Okay. What Einstein showed was that there are some effects that come out of this, just the fact that the speed of light must be constant. Here's the first two, and these are called the Lorentz transformations because they were originally thought up by Lorentz and Fitzgerald, and later on incorporated into relativity. First one is that a rapidly moving object actually shrinks in the direction of its motion. Okay. I mean, this is a real physical effect. Let's say you were traveling at a high rate of speed relative, close to the speed of light relative to my reference frame. You would be shrunk in my reference frame. You wouldn't feel it, but you'd be true. The second one is that in a clock ticking in your reference frame, as you're moving very rapidly, would take longer in my reference frame to tick than it did in yours. And the example that's always given here is that let's suppose you have a clock which is really made of two mirrors and light is bouncing back and forth between those mirrors. Now we'll hypothesize that they're far enough apart from each other that light takes a second to go that whole distance. Okay? And so you can count those times that it bounces, and that's your clock. Okay? And that's what it will look like to you, because the clock's stationary with respect to you, but you're moving at a high rate of speed relative to me, and when you do that, the light has to go a farther distance to make the bounce, and a farther distance to make the second bounce than it did in your reference frame, right? And what that means is, because the speed of light is constant, your clock runs slow. Okay. So those are the first two effects. Before we go on any farther, I want to talk about what does it mean to be moving close to the speed of light. And so, I mean, people say, well, you know, speed of light is such and such, but I wanted to give you some examples of what the speed of light means. There at the top row is travels, everybody knows this, 186,000 miles per second, which is 300,000 kilometers per second in Puerto Rico. And what that comes down to is 1 foot in a nanosecond. So light travels about that far in a billionth of a second. Okay. Although people talk about the speed of light in a vacuum, the speed of light in air is very similar to the speed of light in a vacuum. So we don't have to modify our ideas there. Those of you who have Cat5 cables in your house for video or TV or whatever, the speed of light in a cable is a little less than it is in a vacuum or in the air. It's about 2/3 of what we consider to be the speed of light. And so what does this mean? It means light from the moon takes about 1 1/4 seconds to reach us. Okay. Light from the sun takes about 8.3 minutes to get to us. Everybody says, well, the sun could be blanked out and we wouldn't know it for another 8 minutes. That doesn't mean anything, of course. But it is true that it takes light that long to get to us from the sun. 4 hours from Pluto, roughly 4 hours from Pluto. And the nearest star to the sun, 4 years. But this is an absolute speed limit in the universe. Nothing can go faster than that. And so you will not ever learn anything about that nearest star in less than 4 years from when it happens at that star. Okay, now let's say a little bit about Michelson, because he was the first to give a very good measurement of the speed of light. In fact, it was so good he got the Nobel Prize for it. Again, people get the Nobel Prize oftentimes for an experiment or a theory that was different than the one that they're finally known for. Okay, third effect. We have two now. Here's the third. The mass of a moving body increases. Okay, so if you want to lose weight, don't go up close to the speed of light. And there's the equations. I'm not going to ask you to give me the equations back or to use them in any sense, but I want you to note that they're very similar. They all depend on the speed of velocity and the speed of light in the same sort of way. And so physicists, being lazy and not wanting to write v over c, 1 minus the square root of v over square root of c squared times square, they have given these symbols of their own. V over c, velocity with respect to the speed of light, is beta. 1 minus v squared over c squared to the minus 1/2 is gamma. And as beta approaches 1, gamma approaches infinity. You can figure that out. So, going back to the equations that we just had seen, the time dilation is dependent on gamma. Okay. Length contraction becomes 1 over gamma. Relativistic mass increase is gamma. Now, people often say nothing can go travel faster than the speed of light. Why do they say that? Because as you go faster and faster, or something goes faster and faster, its mass increases to the point that if it were going at the speed of light, its mass would be infinite, and it could not be accelerated anymore. Okay. So, and that statement is still applies even today. Okay, for everyday speeds, I'm not going to say that 120 miles per hour is what you're going to drive every day, but let's say you're driving 120 miles per hour, then beta is this number here. You can write it in scientific notation if you want to. I just put it out in all of its glory here. And gamma is this. So that's how much your mass increases. Even taking the Earth's speed around the sun, which is what Mike and Morley were trying to measure, beta is still very small and gamma is still very small. So all of this stuff is only really applies for relativistic speeds. Okay, what's a relativistic speed? Something that's close enough to the speed of light that gamma is not almost identically 1. Okay, you say, well, who cares if it's not important in our everyday life? Well, our everyday life now depends on things like the GPS satellites, which have to keep excruciatingly good time, and they have to take account of relativity, or they don't work. Okay, a fourth effect. Okay, 3 is not enough. Fourth effect is a relativity of simultaneity. That is, things in one reference frame may appear to happen at the same time. They will not in a moving reference frame, a reference frame moving with respect to that. And this is the example that Einstein gave, and it's the one everybody uses, so why not? In this picture, time goes from the bottom to the top, and down here we have these 2 observers. The blue guy is moving, the green guy is not moving. They're at the same point at this time, and at that time, 2 events go off that are equidistant from that point, and we'll call it an event A and event B, and the light from those then will converge on the observers. Okay. Short time later, the blue guy has moved some. Okay. And in fact, sometime later, he will have moved enough that the light from this front event actually reaches him, and he says, "Oh, that's happened. I know that happened." Hasn't reached the other observer yet. Sometime later, the light from both of these reaches the stationary observer. At the same time, he says, "Aha, they're the same distance away, there's the same time, so they're coincident, they're simultaneous." But the light from the back event doesn't reach the moving reference frame until later. And so when it does, when it finally reaches this guy, he says, "Well, that was some, there's some time interval there between those 2 things." In other words, he sees these 2 events as not being simultaneous. Both people are using the same clock. They're using the speed of light and the distance of the objects, or whatever, of the events. And so what seems to be what is simultaneous in one reference frame If it's in two different places, will be not simultaneous in another one. And this is really mind-blowing. People say, gosh, how can that be? They're not simultaneous anymore. Well, it turns out there's no effects, observable effects of this. I mean, you don't get things out of sync where one thing happens long before the other in one reference frame and so on and so forth. But it is an effect, and it has to be taken into account. Okay. So let me say just briefly, talk about a different test of special relativity than we've been talking about so far. There's these particles from outer space, cosmic rays, called muons. And we can measure their lifetime in the laboratory, and it is 1.5 microseconds. Okay. But on the Earth's surface, we actually see some of these from outer space. Whereas, if you take that lifetime, they should have not got through enough of the atmosphere by the time they decay for us to be able to see any of them. That's the non-relativistic calculation over here. Says for each million, we should only see 0.3 of 1. Okay. If you take relativistic effects into account, that is the change in distance in the reference frames, the time dilation, you get the surviving number being 49,000 out of a million, easily observable. And that's what was done in 1940. There are many, many other tests of special relativity that I'm not going to talk about. Okay. Now, interestingly enough, in special relativity, there's this thing called a space-time interval. And what it says is, if you take the time between two events, call that time delta t, and if you take the distance between two events in any reference frame, and you subtract the square of the distance from the square of the time, you get a quantity that is the same as it will be measured in any other reference frame. So this is another constant besides the speed of light. This is the basis of what we call the space-time continuum. Space-time interval is this time here, squared minus this. And people usually like to draw this in a picture like this, where there is the present time, and there's where you are. Here's your past down here. Here's the future up here. This is the times arrow, okay, as it goes that way. And as you move through space, you follow something called the world line. You've been doing that all your life and didn't even know it, right? Okay, but the world line can't go everywhere. It can only go within what's called the light cone. It can't go out here because that would mean you were traveling faster than the speed of light. Okay. So this is actually divides space up into things that can affect you, or things that you can affect, and things that are of no consequence to you because they won't affect you. You can't affect them. That's what we call elsewhere. All right. Okay. The guy that discovered this is by just combining Einstein's equations was Hermann Minkowski, and here's his famous quote: "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows." Isn't that correct? "And only a kind of union of the two will preserve an independent reality." He said that in 1907. You know, it took him a couple of years to work it out from Einstein's equations. So he really discovered space-time, and what we'll talk about a lot in general relativity is the space-time continuum. Okay, so Einstein seems to have been right with special relativity. All these People have been testing it for years and years. Why was he right? Because his fundamental thing that he used was this fact that the speed of light in the vacuum is the same regardless of the observer's motion. Okay. Which is from Michelson-Morley. He took that as his basic fact. And then he chose consistency. If this is true in any reference frame, it has to be true in other reference frames, then all the observed physical effects must happen in both reference frames, and therefore there is a reality. Every reference frame will have its own observed reality, but all consistent with the laws of physics. And he was not afraid to carry his reasoning out to its logical conclusions. I say logical conclusions. You can come to a lot of illogical conclusions from something like this. And he wasn't afraid that they might be counterintuitive. In fact, they were. Okay, now, jumping back to me. I graduated high school in 1966. 1967, radio pulsars were discovered by Jocelyn Bell in England, who did not receive the Nobel Prize for it, but should have. Okay. Just the things is that pulsars are such good timekeepers that until we invented atomic clocks, we didn't know that they were not perfect. Okay. And so you can actually use pulsars to keep time for you if you have the, you know, you have their characteristics and so on. So this happened. Radio pulsars were discovered when I was an undergrad. In 1974, I obtained my PhD from the University of Arizona, and my thesis was on a special relativistic model for the polarization of pulsar emission. Okay. I won't go into that much, but anytime there's something being beamed in physics, it's usually because of relativistic motion of the source. And we'll let it go at that. Okay, so I made extensive use of predictions of Einstein's special theory of relativity in my PhD thesis. Okay, this is all special relativity so far. How about general relativity? Well, we haven't talked about that because up to this point in our narrative, Einstein hadn't invented it. Yeah. Okay. What it does is it takes special relativity and applies it to even accelerated reference frames. Okay. Now he's saying the laws of physics have to apply in accelerated reference frames if you take general relativity into account. Now, one of the things that Einstein showed was that gravity is the same as being in an accelerated reference frame. I think you may have seen pictures of, or movies of somebody in an elevator being lifted up, being accelerated, and thinks that, you know, a ball falling to the floor is due to gravity, but it's really due to acceleration. That all that stuff is in this theory. So because gravity is the same as an accelerated reference frame, and Einstein figured out what the accelerated reference frames did, he found out what gravity does. Okay? So, and what is gravity? In the end, we think of it as a curvature of this space-time continuum that Minkowski talked about. There's a picture of one of his first papers about general theory of relativity. His final paper came out in 1916. And you've seen this demonstration as well, or something like it. And I think they've got something set up out here in the hall that you can do that kind of experiment. A curved reference frame, which is what this is, things will tend to orbit around a place where the curvature is greatest. And so Einstein was saying that the curvature of space-time is greater around objects that with mass More mass, the more curvature, and that's what actually causes things to orbit them. Here's his final paper on this, Annals of Physics in 1960. Okay, so everybody has fun with this. In fact, you know, if you go to the mall or something, you'll see these things set up with these cones that you can roll coins around. And they orbit the center because space-time is curved there. So anytime you have a massive body, space-time around that is curved, and every little body causes some curvature. When you move within that, bodies follow the path of the least space-time interval. Now, in the extreme case, space-time is so curved that there's a hole in it. That is, there's one point in space where the curvature is infinite, and light can't get out of that, and that's why it's called a black hole. Here's an example, you know, a two-dimensional example of what that might be like, where there's this point where the curvature is infinite. It's called singularity. Light can come out of this, except if the curvature is great enough, it can't get out all the way. All the light that comes out is redshifted somewhat, but when the curvature is high enough, you get no light out because the redshift becomes infinite. Okay. Now the person who thought of all of this kind of stuff about black holes and so on first was Carl Schwarzschild. He took Einstein's equations. This came out in 1916, right? In 1916, he published what the metric around a black hole had to be like. And this is the space-time interval squared. This is the time squared. This is the distance squared. There's another factor in there. And when you use all of this, you come up with something called the Schwarzschild radius. Schwarzschild radius is the radius from the center of a black hole where light cannot escape anymore. Okay? So everything inside of that is hidden from you, and outside that radius, it is not. So this is called the Schwarzschild radius. After him, who knows what he might have come up with. But he was killed in the First World War only months after he published this. That was the end of him. Since that time, black holes have been discovered. We know now that there's a black hole at the center of our galaxy with a mass of about 4 million times the mass of the sun. You say, wow, that's a lot. No. Many other galaxies have black holes at the center billions of times as massive as the sun. So this curvature of space-time is real. The first black hole that was discovered is something called Cygnus X1, where X-rays come out, but they come out outside of the Schwarzschild radius, and it has a mass of about 15 solar masses. It's actually a double star. Okay. Well, the first confirmation of Einstein's general theory of relativity was due to Sir Arthur Eddington. And there's a picture of Eddington and Einstein. That's a little after he made his discovery. It was 100 years ago, actually May 29, 1919, on the island of Principe off of the coast of Africa, where these measurements were made. Here was the idea. The sun is massive enough that light going by it should be bent by the curvature of space-time. But not much. Like 1 3/4 seconds of arc. Very small amount. Furthermore, how are you going to observe the light going by the sun, by the edge of the sun, because the sunlight will block the light, will swamp the light of the star. Okay, so what you do, of course, easy to say now, is you wait for an eclipse of the sun, where the moon is actually blocking the light from the sun, the sky becomes dark, you can see the stars, you can measure their positions. But measuring the positions there, or that time, is not sufficient. You have to know what they usually look like, okay? Which means, and this was true of Eddington's experiment and all the other experiments that do this, you had to go to Principe or wherever it was 6 months earlier and take a picture in the night sky of the same stars so you'd know exactly where they were in the sky, right? Then when you overlay the two stars, what do you find? If the light from the star is bent by the sun, here's the actual position of the star, and the light gets bent like that, and that means that looking out here, you think that the light's traveling straight lines, you think that, and you think that's where the star is. That is, in fact, where it apparently is for you. And when Eddington did this, he came up with a number almost exactly what Einstein had predicted. An amazing result showed that light actually is bent by the sun and bent by the same amount as Einstein had predicted. Okay, well, there are other things in the universe that bend light a lot more. For instance, there are very massive galaxies, and there are dark matter galaxies, and those things can bend light so much that they act like a lens. And these are actual photographs of the sky, certain parts of the sky, where light going by an object here or here is bent such that you see this ring. These are called Einstein rings now. And so they're another example of gravitational bending of light. Okay. We're getting there. Now, as objects orbit each other, they lose gravitational energy. How do they do that? Well, every mass, of course, is warping space-time, and the two objects that are going around each other are disturbing space-time in such a way that waves of space-time travel outward at the speed of light, like in this picture, where you can imagine that the two objects are in here close, and the space-time, as it's bent, moves out at the speed of light. Okay, this has the effect that the objects, as they lose energy in this way, will gradually come closer and closer to each other, orbit closer and closer, and finally, maybe, collide. Okay. These so-called gravitational waves have been now the object of 2 Nobel Prizes. The first one was awarded to Hulse and Taylor in 1993, where they had discovered a binary pulsar. That is a pulsar that was in orbit around another neutron star. These two things were orbiting very close to each other. They're massive, moving around each other. They emit gravitational radiation, and as they do so, they should come closer and closer. If pulsars were not such good timekeepers, we wouldn't be able to tell that at all. But what that does is it affects the time of arrival of the pulses for us, and how that happens is the basis of this Nobel Prize. This is the actual shift of the orbit due to general relativity. This is the calculation from general relativity. These are the data points. I challenge you to come up with a better fit than that. Okay. And this is over a period of, 30 years? Okay, this is Joe Taylor, nicest guy you ever want to meet. If you ever get a chance to meet Joe Taylor, take it. Okay. And I was lucky enough when I was in Arecibo in 1982 to be on the team that corroborated Paulson Taylor's first measurements of this and showed that, yes, indeed, it agreed with Einstein's prediction. And that's why they got the Nobel Prize, because we corroborated their measurement.
That's right.
Okay. So I keep telling people, you know, even if I don't get the Nobel Prize for this, I should get the No Whistle Prize. Okay. Blast from the past. This is the radio astronomy staff in 1980 at Arecibo. My hair was a little longer then. I was a little thinner. And this is what Arecibo's platform looked like in 1982 when these measurements were made. And you can see that the Gregorian was not there yet. We actually did this corroboration with one of those line feeds sticking down off the bottom of the carriage house. So that was the first Nobel Prize that was awarded for gravitational radiation. Second was the discovery of gravitational waves themselves. And how is it done? With an interferometer. Okay. Now this is a little bigger interferometer. It's like 20 miles long path for the light to go. But it's the same thing. Light's going this way, light's going this way. You're interfering the two things. In this case, because space-time is actually being contracted and expanded by the moving gravitational radiation, you can see that in the signal, if you get a signal. And so what you need is something that emits gravitational radiation very well, and that means colliding black holes. Okay, you get colliding black holes, you get enough gravitational radiation that you can actually see the change in the size of these arms in the interferometer, and that was the basis of the second Nobel Prize for this 2017. One of my friends at the Air Force Research Lab was on this team when he was a graduate student. It was years later that they gave the Nobel Prize, and he was like, you know, his name was so far down on the list of authors of that paper that you couldn't even find it. But anyway, he was part of that. And since that time, and since the time of Eddington, more tests of relativity are being done every day. Some involve satellites as they orbit the Earth. Others involve large telescopes like the Arecibo Observatory. Einstein has passed every test. Imagine if somebody expected you to pass every test for 100 years. Well, Einstein could do it even after he's dead. Okay, now I promised you I'd talk a little bit about the global GPS, global positioning system, because this is the basis of our modern civilization. I have to tell you that. The time you keep on your cell phone, on your watch, everything, your positioning on the Earth, GPS and so on, is all dependent on these satellites. And they're dependent on the fact that the speed of light is constant. What they do with the GPS is that they have all these satellites out there and they know exactly where they are. Okay? These satellites are sending out signals all the time. Your cell phone or GPS unit measures how much delay there was in that signal reaching you from the different satellites and triangulates your position, and that's how you know where you are. And in order to do that, they have to have exquisitely accurate clocks, 1 nanosecond a day. Okay, that's good. That's that far. I can travel that far. Okay. So you compare time signals from the different satellites. They're moving at a high rate of speed. Of course, they're farther out in the Earth's gravitational well, and so you've got two different kinds of relativistic effects going on here. Special relativity says, because these things are moving so fast, they will run slow, right? Time dilation. They'll run slow by 7,000 nanoseconds per day. That's quite a lot. General relativity says, well, these satellites are outside of part of the gravity well, and so they should run, the clocks there should run faster than they do down here because we're slow, because we're in a gravity field, okay? And there's the equation. You can work it out if you want. It comes out to be about 60,000 nanoseconds per day. So the one effect is saying things should run slow, the other is saying things should run fast. If you get any of these off, in one day your position from your GPS will be off by either 1.4 miles or 12 miles. Okay, you drive right into the ocean. Okay, so GPS positioning depends on both types of relativity to work at all. Okay. So it does impact your everyday life. And every day now, every clock that you read is set by reference to GPS time. Okay, my final slide and my final aside is that Einstein is still in my life. Right now, during this 6 months and for the last few years, I've been observing radio frequency interference, what looks like interference, at the Arecibo telescope that comes from arcs on GPS satellites. You know, GPS satellites, like all satellites, have these big solar panels. Because there's a high voltage on the solar panels, an arc, that produces radio emission, and I've been looking for that. And so I'm 70 now. Einstein's still in my life, and I think he's in all of your lives too because of the GPS. So I was 7 years old when Einstein died in 1955. But his science is still as good today as it was then, as it was in 1916. So I think it is remarkable and worthy of celebration that Einstein has withstood 100 years of tests and is still going strong. That's it. So, thank you all for coming. Final words? No. Well, you can ask questions if you want. I just don't want to keep people from getting wherever you want to go.
Thank you very much to Dr. Ferguson.
So we have like a little section for questions. If anyone has any questions,
Ask me anything. I'll give you an answer even if it's wrong.
Maybe about the universe, a general question
Do
about.
you ever stop to imagine what Einstein could have done if he had at his disposition the equipment that scientists have today?
Well, he was a theorist. So he wouldn't have done much, but there are other people around him, the observers, the experimenters, would have done a lot more. I have to say this about Eddington. You know, we're celebrating his observations. These are probably the only observations that Eddington ever made in his life, because he was a pure theorist as well. But he was a theorist that knew Einstein's theory so well that he could set up an experiment like that would be able to measure this tiny little bit of light deflection. I don't know what Einstein could have done. You know, it's like, you know, I don't know what I could have done had certain things not happened in my life. But he did enough, don't you think?
Oh.
Okay,
We have another question over there.
okay.
Hi. What are your thoughts about radio astronomy and how you think we can implement that information on radio astronomy?
How we can do what with the radio astronomy?
Implement that information on radio astronomy.
Okay, yeah. Well, right now people are working really hard to try to see gravitational radiation by using pulsar observations at Arecibo. But what they're doing is they're looking for the change in distance between us and a pulsar caused by the gravitational curvature of space-time. Okay, so that's one way. People are thinking of new ways all the time. If you're clever enough, you can think of a way to use radio astronomy to do this, or some other kind of astronomy, or your laboratory experiment, or whatever. Let me say this about the Michelson-Morley experiment. Since it was first done, people have been trying to show that it was wrong for up until now. They've done things like they've evacuated the whole area where they were doing the interference, and so it was a vacuum. Didn't make any difference. They put the whole apparatus in water. Didn't make any difference. There's an infinite number of possible ways you can experimentally determine something or determine that it doesn't work. And I'll leave that to you. You people are smarter about that than I am anyway.
Is there a relationship, if any, between the time-space fabric and dark matter?
There's a relationship. The question was dark matter. Dark matter bends space-time just like regular matter does. Okay, and that's in fact the only way that we know of detecting. People have even, I showed you some of these pictures of the Einstein rings. People are now using the deflection of things in the background to actually detect dark matter. So the relationship is the same as between ordinary matter and gravitation, except that there's probably 10 times as much dark matter as there is ordinary matter. So I expect that we'll see lots of things, maybe Einstein rings where there's nothing visible, something like that. I don't know. But as far as we know, there's no difference between the matter being dark matter or ordinary matter like we know and love.
Thank you.
Any other question?
I have a question between the light property. If the object shrink at the direction of the motion
Yes.
of the light, and mass increases as long
Yes.
as the speed increases, would
Yes.
that make the object more dense?
Yes.
Therefore,
To
by
you.
making it
To you, yes, it will make it more dense. This is probably a good time to talk about this shrinkage and the passage of light. How many of you know about the aberration of light as the Earth goes around the sun? You can actually see positions of stars in the sky apparently change because the Earth is moving toward them or away from them. And what that does is it makes the light from them appear to be just changed in its direction. Okay. Well, it turns out that this business of the apparent rotation of a moving object is just the aberration of light in reverse. If it's moving very rapidly, what happens is you only see it by light that's emitted more toward the back. Okay. because it's aberrated by the motion, you know, toward the front of the motion, and so this, but you don't get the right numbers if you just put in the Newtonian equations. If you use Einstein's equations, then you get the exact apparent appearance of the object, and it does look like it's rotated in the direction of its motion, which means if something's going really fast with respect to you, you're going to see the back end of it no matter what. Okay. So anyway, it's all related. It's all the same physics. Somebody way in the back.
Yes. Space-time interval is the solution for human evolution, knowing the fourth effect of relativity.
I didn't get all of that. Something about evolution and space-time.
I'll repeat it again. Is space-time interval the solution for human evolution by knowing the fourth effect of relativity?
I don't know the answer to that.
I'm asking because the space-time interval is itself the universe,
Yes.
and humans are basically connected with the universe. It is possible that the universe alters life itself by the decisions that we make.
Not much. Let me put it that way. Unless we blow ourselves up, and then that could be a local disturbance in space-time. All of this that I've been talking about, Einstein rings and so on, is an interaction between human beings and the universe. Now, most of the times it's, you know, light from other places in the universe, and we interact with it here. There's no reason why, you know, our actions here couldn't affect the rest of the universe, but only in the same way, same kind of way. You know, light from us is going somewhere else, and so on and so forth. I often talk to my students about it, show them a picture of the Andromeda galaxy, and say, okay, this is more or less what your galaxy looks like to somebody in Andromeda. Okay. So yeah, it's all one fabric. Now, recently people have been talking about, and you probably have heard about, quantum entanglement, where you take two particles, create two particles at the same time, and they will, no matter where one of them is measured, the other will be measured to have certain properties related to the first. Okay. People have said, well, doesn't this violate relativity? And the answer is no, it doesn't, because there's no information traveling from one of the particles to another. You've got people in different places measuring those properties, so there's no information, and it's really, Einstein's theory really applies to that information. Now, what quantum entanglement is important as is an example of the relationship of everything in the universe to everything else. Okay. So, to answer your first question, yes, you do affect the universe, and the universe affects you. It's all one universe. Okay. Now, your effect on a galaxy 13 million light years away will only happen 13 million years from now, but aside from that, the light from you is still traveling through space, you know, at the speed of light, and will eventually reach there, and maybe they'll be able to detect it. So it's all one universe, it's all one physics, everything is related to everything else, and physics is really about finding those relationships between two different things, or between energy and matter. All those relationships is what physics is all Okay, I think we better call it quits.
But let's thank you again, Dr. Ferguson. And we would like to give you a small present from here from the university. Thank you for
Goodie
coming.
bag. Oh, I love all this. Okay, thank you very much.
Thank you. Thank you very much for coming to the tenemos por aquí, ahí en una mesa, tenemos un paciente sobre el universo, los que lo quieran tomar, están bienvenidos de tomarlo, tengan ese tiempo.
Sí, pero ya, pero no pueden el próximo martes.
Pero yo lo leí en inglés y no decía por poner recibido. Y porque yo lo chequeé. Para estar seguro, porque era lo primero. No.
No, es que yo les mandé otro correo a ellos, porque ellos tenían para mañana que hacer un nuevo procedimiento con ustedes no lo hicieron para aquí, yo les mandé a uno. Ustedes no me dijeron que eso.
Yo te pregunté, pero...
Yo les dije un martes, pero sí que este martes está ocupado.
Ah, no puede ser...
Al próximo está ocupado, entonces sería el próximo.
Es que llevan el papelito que ponemos.
Sí, el papelito. Ay, bien, sorry.